So we have Tim Mattson again this morning, and into the early afternoon before the contributed session. He will be talking this morning well, he'll be continuing his lectures from the other day on OpenMP parallelization of programs. So take it away, Tim.
All right, here we go. I think this is where we ended. So let me get my screen size
Let me
here.
say while Tim does that, we'll be continuing to use Discord channels for questions, and anybody in the classes should feel free to both ask and answer questions, and Tim and others will monitor that. So
yeah,
go
and
ahead.
given the amount of participants on Zoom too, so it might be doable also to interact, to just unmute your mic and interact with team verbally, not just via text. Okay.
Yeah, that's true. I don't mind people cutting in verbally,
Okay.
When I do this interactively face to face, I tell people I want the room to be noisy. Lots of people talking and cutting in. So yeah, and the goal here is, even though we're on Zoom, to try and get as much that interactive feel as possible. So gosh, please remind me, isn't this where we finished yesterday? I gave you the exercise with pi with loops. So now
Yeah, I think this is it.
This is it, good. So now I would look around the room and I'd say, hey everyone, let me make sure, I'm sorry, let me get this chat channel up so I can see it. Okay. So now at this point, I would call out to everyone and I'd say, hey, how many of you finished the exercise? How did it go? And we can't do that. So I'm gonna have to assume that everyone said, oh yeah, we did this exercise and it's cool. So I'm gonna assume you've done this exercise. I hope that's a good assumption. So I'm gonna show you my solution. So start from the original pi program and parallelize it with the loop construct and minimize the number of changes you made to the program. So, the idea here is every time, this is just a general truism of software, unfortunately, every time you make a change to a line of code, you create an instance, another opportunity for introducing a bug. So minimal changes is like a really good thing, okay? So here's my solution. Oh, get back on the screen. You didn't think I'd have this down by now. Oh, I went too far. Oh, okay. So here's my solution. It's delightfully simple. Pragma OMP parallel. I still need to make sure that that variable X is private to each thread. So I declare double X inside the Pragma OMP parallel. Then I have Pragma OMP4 reduction. And I take advantage of the fact that it's going to make the loop control index private by default. So I don't have to do that by hand. And then of course, sum, it's going to make private because of the way the reduction works, but then it'll combine it with the global. So that's it. I added the pound include and then a pragma, a couple brackets. I didn't add much at all. So wasn't that wonderful? Now, here's an interesting point, and I don't want to belabor it too long, but young folk, which most of you, I guess, are, would have done it this way. And this is a better solution. Pragma OMP parallel 4. See, the only reason I did the Pragma OMP parallel separately is I wanted to declare X as double. So I had to leave myself room to declare variables that I wanted private to each thread. And so that's why my solution looks like this. But people today are taught in C. C lets you put declarations anywhere you want. And why not just put the declaration of that double inside the loop? Now, I look at this and I want to throw up because it's like, no, I remember the old days where if you did that, it would declare a new variable each and every time, which, we got large number of steps, probably kill your performance. What you're doing with this solution here is you are depending on the compiler to be smart and to look at this code and go, oh, we just declare double once. So you're depending on the compiler to do the right thing. And virtually every single C compiler you can get your hands on today indeed does the right thing. So I would have to say that this is probably a better solution. 2 lines of code is all. And one of those lines of code, the pragma, of course, is ignored if the compiler doesn't have OpenMP enabled. And so this is the power of OpenMP. And I would say to the majority of OpenMP programmers, this is all there is to OpenMP. Find the loops, put a pragma OMP parallel 4 on the loop, and you're done. And you leave an awful lot on the table if you don't use the richer palette of what it provides, but this is it. So isn't this cool? This is just really awesome. And if I run it, I get pretty decent performance. You know, it's not quite as good as my my SPIMD code that I optimized, you know, so it's, you know, it's not always the ultimate performance. There's a little bit of overhead in managing a loop, but not much. And when you start getting to realistic size problems, you don't even notice that overhead. So that's really cool. Now, there's a couple more little details. Well, let's just say one big detail I'll cover now. Remember, at the end of the loop, there's an implied barrier. So what I want to talk about is those barriers. Now, in synchronization, we've discussed 2 different synchronization constructs, the critical and the barrier. And in the barrier is just a brutal, it's like taking a sledgehammer to your performance. You know, it says all threads wait here. Okay, now you can all go forward together. So in terms of disrupting your performance, barrier is brutal. So look at this example right here. I have 3 big old arrays, and I'm going to create a team of threads, pragma OMP parallel. And so there's no reason I can't mix SPMD style programming and loop level parallelism in the same program. So here I go. Int ID, OMP get thread num, so I know my ID. And now everyone's going to do a big old ugly calculation and fill an array A. And then I look ahead in my program and I notice, hey, I'm going to use that in the following loop. Okay, that means I have to make sure everyone is done before anyone goes on. You got to put a barrier there. So I put an explicit barrier there. Okay, after that barrier though, we're now going to fill the array C, and we're going to do that together in parallel. So I use a pragma OMP4. Okay, that's cool. I look ahead and I notice that the following loop is going to use C. So, okay, there needs to be a barrier. Okay, fine. OpenMP recognizes that typically it's safest if you have a barrier there. So we put one there for you by default. So this is all cool. It works really well. So we put it there by default. Now we look at the next loop and notice it's creating an array B, which is not used later on. So that barrier at the end of the loop would actually be excess synchronization. And you want to synchronize when you have to, but no more than you have to. So that's what the no wait clause does. No wait says it's available for every work sharing construct. And we'll have 1 or 2 more work sharing constructs. One we'll talk about, you know, but there's several work sharing constructs in OpenMP. And every single one of them imply that barrier at the end of the construct. And so they all take a no wait, which says turn off that barrier. So now if I go pragma OMP4 no wait, I do that parallel loop and I don't take that barrier. I immediately go on and start my calculation on A. So that's how no wait works. Now there is a barrier at the end of the parallel region. There's no way to turn that off because we can't conceive of a parallel multi-threaded program where your correct performance correct behavior wouldn't require that barrier. So there's you can't put a no wait on the pragma OMP parallel. It just refers to the 4. So that's the no wait clause. But also the purpose of this was also for us to get a chance one more time to discuss barrier synchronization. It works. When you need it, you use it, but gosh, don't use it any more than you have to. All right, now we get to a next fun section. And then we finish it with a really juicy exercise that everyone loves and hates. We'll see what I mean. The data environment. And so far we've gone just with the default rules. And you can do an awful lot with just the default fuels of the data environment. That, most variables are shared by default. If you declare them outside the construct, they're shared inside the construct. That mindset covers most cases. Global variables are shared. So for you Fortran programmers out there, common blocks, variables that you declared as save variables, module variables, those are shared. All of the threads have access to those variables. In C, file scope variables. So those are the variables. If you think about my Pi program, I don't know why I started doing this, but I do. I declare the number of steps before main. If you declare the variable before the main, it becomes a file scope variable. So file scope variables and variables you declare static are shared. All the threads will see them. The other thing is if you dynamically allocate the memory. So if I'm grabbing my memory with an allocate in Fortran or a malloc or a new in C, it's shared. And if I'm teaching this as part of a semester length course, we spend an awful lot of time talking about the architecture of threads on a modern operating system. And of course, we don't do that here. But let me just mention, you have a process. The process is the high-level unit of management of a running program by an operating system. The process is a region of memory managed as a heap. And then all the threads belong to the process. So the way to think about this is all the threads are managed by the process and all the threads can see the heap. Now, anytime you launch a function in a thread, you start up a thread and it executes a function. So that function case includes threads. They have their own private piece of memory that's managed as a stack. So if you're ever trying to remember and keep track of this, for those of you who are more computer science oriented, if the variable comes off the stack, only the thread can see it. If the variable comes off the heap, all of the threads can see it. And that's really, from a computer science point of view, going probably lower level than most of you want to go. That's the rhyme or the reason behind this. Anything off the heap is shared, anything off the stack is private. And that really is the general principle. So just to drive home the obvious, here's an example. So I have an array that I declare, and I'm declaring it before the main. So it's a file scope variable. Then I declare an array index before the parallel region. Then I have a simple parallel region with only one line, pragma OMP parallel region with one function call. That's why I don't need the brackets. And then that function call is over on the right side. And that extern, for those of you who aren't really into C, that extern is just something you're telling the compiler, hey, compiler, you're going to find this variable on the heap. You're going to find this variable in the global space. So relax, it's coming. Because C is a strongly typed, well, let's say it's a strongly typed language. And we can argue about the word strong for those of you who might want to. So you have to declare the types of everything. So extern double says, hey, compiler, that's coming somewhere else. Don't worry. So then we pass in the index, and then I have a static int count. And so you can see that prior to the parallel region, a, index, and count exist. As the program's compiled, those are all put on this heap. They exist. Once I get inside my program, I declare double inside the function, so it goes on the function stack. It's private to each thread. When you go out of scope, that variable goes away. Okay, when the function stack, when that function with the stack goes out of scope, its stack is reclaimed, all that goes away. So after the function's done, the array temp goes away, but a, index, and count remain. All right, now, of course, now that you deeply understand the default rules, let's talk about how to change them. And we have a set of clauses that you can add that let you change the storage class of the variable. And there's several of them, but the ones you use, remember, my whole philosophy is OpenMP has gotten so big, I just focus on what people actually use. So there's shared, which is the default case, right? It says These variables in this list will be shared inside this parallel region. There's private, which says I will make a copy of each of these variables for each thread. And then there's first private. Now, private makes a copy of the variable, but it doesn't initialize it. First private does initialize it. And for you C++ people, it uses the copy constructor. For you who are not C++, ignore that statement. It's confusing. You don't want to go there. And you can put these on parallel and for constructs. And then there's one more, which is actually really handy in debugging, called default none, which basically says you must declare the status of every variable. Okay, that's how it works. So let me be clear here, and I'm going to introduce a little piece of jargon on this slide. Here's an example of private. So if I have private and then a list of variables, it says to make them private. And now here's the piece of jargon. Look at that pragma. Pragma OMP parallel 4. And when I have that loop embedded there, remember the loop control index of the parallel loop, which would be I, is made private by default. But if I have a second loop inside there, then it's up to me what that is. That J of that second loop is not made private. It's not a parallel loop. It's just a piece of code. So to OpenMP, there's nothing special about it. So I have to make it private. This is one of the really, really common errors that people make, is they forget to make that loop control index J private. Now, J is a symbol. It is a token, right? It defines a variable, a location in memory. That's what a variable is. When I have it in the private clause, it has to exist, right? There has to be a variable in order for it to be in the private clause. We call the variable that existed prior to the construct of the clause the original copy. All right. So if I'm ever in a conversation and I need to disambiguate, well, we have J inside the loop, inside the parallel region. That's the private copy. And then we have the J that existed prior to the loop. It's still called J. So I need another name for it. I call it the original variable. All right. It's just sometimes in talking, I can't avoid that piece of jargon. I need to refer to what was the variable before. You know, it's the same name, but what was it before the construct? It's the original variable. So that's a piece of jargon. All right. So that's how you use private. But remember, private is not initialized. So look at this case here where I'm going to sum up into a variable. Of course, there's other problems with this because I'd have a race condition if it was shared, right? So I've got to make it private. So now I'm going to count how many iterations did each loop actually get. And this is really useful when you're using like the schedule dynamic, so that you don't know up front how the static distribution is going to work, and they're going to dynamically get them. So sometimes you want to counter so you can keep track of how many iterations you actually got. At any rate, it's not initialized. So this program's in error because temp was never initialized. So remember, private gives you a private variable, but it does not initialize it. Now, when you go out of scope, the variable in question that was privatized goes away, right? It's a private variable, acts just like any other, it goes away. So that last print statement reverts back to the original variable, so it will print 0. Okay, now I look around the room and I look if anyone's confused, has questions. Oh, okay, no questions? Good, onward. Oh gosh, there's a miserable case here, and it pops up now and then. And this case is so ugly, we specifically say that this is illegal. I'm sorry, I used to like to skip this, but it does show up, so I don't skip it anymore, so bear with me. This specific instance is illegal. So I have a file scope variable, int temp, right there at the top of the code block on the left. All right, so now I got my function, and I'm going to initialize that global file scope variable to 0. So now I come into a pragma OMP parallel region and I declare a private temp. Okay, so I have a private of a file scope variable. Now I call a function work, and inside work I reference temp. What the compiler people tell me, and I'm not a compiler person at all, but what the compiler people tell me is there is no way for them in implementing the compiler to disambiguate what address to update with that reference to temp inside work. They just give up. They say, nope, we can't do it. I look at it as pretty obvious, but they say, nope, can't do it. We can't make a compiler understand this. So this is illegal. Privatizing a file scope variable creates a situation of confusion, and you just don't do it inside a function where it's not clear what you reference. All right.
Sorry, Tim, can I interrupt you to go back to this slide?
Yeah.
Hi, by the way. On the right-hand side where you have the extern int TMP, why is that ambiguous? You have clearly said it, but why is it ambiguous that TMP is not referring to TMP equals 0?
I know. I don't know. I have to tell you, I don't know. The compiler, that's why I said, the compiler people tell me they can't disambiguate. As a human reader, we have no problem. It's really clear, isn't it? But because it's the same name, and because in that code section that they're working with, you have two different things referenced by the same token, it confuses the compiler. And you know, it's fascinating working on a standards committee like OpenMP, because I'm more of a physics and chemistry guy. In fact, I have never had a class in computer science in my life. I've never taken a compiler course. You know, I'm not the computer scientist, but most of the people working in the standard are compiler people. And so sometimes my biggest challenge is just figuring out how to talk to compiler people, because they're different kinds of human beings.
So here you were saying,
they tell me that it's just the internals of the compiler disambiguating the namespace they have to work with inside the compiler. It's just too difficult if I have these two different, because they're different variables. Remember, a variable is just a name for a location in memory. That is all a variable is. And so what they're saying here is now I have one name, TMP, and it resolves to two different locations in memory. And that just freaks them out. The compiler can't handle it.
And this is because TMP was defined for the whole file on the left. I mean, what if you define it inside
defined for the whole program? Remember, it's called file scope. It's declared outside of the function.
Right.
But it's a global for the whole program. And now I've given it a separate name. And both of those names are active and visible at the same time when they get to that function.
You wouldn't do the trick by just using the int definition inside the void danger. Would just be.
If I use the int designator, now I've disambiguated it. I don't know. I think the big problem is the fact that I have a separate compilation unit with work. And when the compiler compiles it, because at compile time, it uses this tag and associates it with the global. And so at any rate, I don't want to spend any more time on this, because the big thing is know about the situation and just don't go there. Now, let me be clear. Programming practice, good C style, is you don't really use file scope variables much. You shouldn't use them much. They're really sloppy. So this situation, if you're a good C programmer, does not come up very often.
Okay, thank you.
Yeah.
Can I ask you a question? Sorry, you didn't want to spend any more time.
I know, I don't want to spend any more time on it, but go for it.
So I have a more fundamental question. Why bother with this private declaration and instead just use another variable, since it's local to the scope or block?
That's right. That's right. There's no reason.
Okay.
Remember, the classic way OpenMP is used is you write a program and it's a serial program, or it's an MPI program, and you verified it and it's working. And now you're going back and adding OpenMP to it. And This comes up more in Fortran because Fortran doesn't let you declare your variable. You can't put variable declarations anywhere you want throughout the code. So all this weirdness with private clauses and shared clauses and all of that, that's mostly there for the Fortran programmers because they can't just declare something right where they need it the way we can in C. So.
Okay, thank you. That makes sense.
Yeah. Okay. So what if I want to create a private and I want it to have a well-defined value? Here I have an increment, and who cares why I'm counting? So, I have an increment that I want to keep track of. I want each thread to have its own value of this. So I want it to be private, but I want it to have a well-defined value. So that's first private. First private, it creates the private copy of the variable, and then it assigns it to the value of the original variable. So this is how I get that well-defined initial value. I used first private instead of private. So here comes an easy test, very, very easy. So consider the following example. I have 3 variables, A, B, and C, each assigned 1. I have a parallel region with these clauses, private B, first private C. So stare at this and have the answers to the following questions. Are A, B, and C private or shared inside the parallel region? So that should be pretty quick. I assume you all have an answer in your head already. And what are their initial values inside and after? All right, think about that just a moment. And here's the answer. A, which didn't appear in any clause, is shared by all threads, and on entry to the region, you see the value 1. B and C, because they appear in a private or a first private clause, are private to each thread. So each thread has its own copy. We allocate a variable on the thread stack, and that variable is named B, and the other one's named C. B's value is undefined because we don't initialize a private. C's value is well defined. It's equal to the original variable's value. It's equal to 1. After the parallel region, B and C, the private copies, go out of scope. So now the name B and C refers to the original variables. The value is 1. And A, because it's shared, its value is whatever happened inside the parallel region to A, or 1. So that's it. And I would look around the room and I'd make sure everyone's nodding their head and going, yeah, I got that. Okay. And this is the time to pause. Are there any questions about private, first private? And I didn't show it. Shared is just a way to you to affirm that, I recognize that A is shared because it's just conferring the default status. I use shared sometimes because, remember, when I put code in PowerPoint, it has to fit on the slide, so it's always little tiny snippets. But if you have a complex program with hundreds of lines and lots of stuff going on, it can really help you to get into a discipline of explicitly declaring the sharing status of every variable you're going to use. So in complicated algorithms, I will sometimes use shared, just to remind myself when I'm reading the code that, oh yeah, that variable's shared. So remember that. You better synchronize its access because it's shared. Okay, so I've mentioned before default none. And gosh, another little piece of jargon. I'm just going to mention it briefly. Default none says that if a variable is not declared explicitly its sharing status, the compiler will complain. So this is a great debugging aid. And for this piece of code, the compiler will complain that J and Y have not been declared. Because notice, Y, which is shared, J, which is shared, because they don't appear in a private or first private or reduction clause. All right. But I didn't declare it that way. So normally this code, of course, would have a race condition on J. It would be a mess. So that's really handy because now the compiler will come back and tell me. If you don't put the default none, the compiler has no reason to tell coming in that there's a problem with the fact that J is shared. So at any rate, default none is a clause that will help you tell the compiler to help you explicitly declare all your variables and find these bugs. Because Having something shared when you think it's private is one of the most common bugs with OpenMP. All right, now here comes a good, juicy exercise. If this exercise irritates you, the person to blame is Mark Bohl of Edinburgh Parallel Computing Center. He came up with this, and I love it. I've been using it for years. There's a program, Mandel.c. It computes the area of a Mandelbrot set. And you have that in your exercise. And your job is to debug it. So it was parallelized with OpenMP, but we were kind of lazy. We didn't really think hard about it, just quickly parallelized it. And so your job is to find and fix the errors. Notice that that word error is plural. There's more than one. If you're one of the people who does this really, really quickly, some of you will, especially if you've had a little OpenMP exposure before. When you're done, optimize it. There are multiple ways to do some of the things inside this code. So that's the exercise. I will be hanging around. You can ask questions either over Discord. This one is another one of these 15 to 30-minute exercises. It can take a while, but it's important. In little brief interlude, I have a quest to try and make people in the sciences better teachers, because many people in the sciences are terrible teachers. I'm sorry, but it's true. You get no education in teaching, so you're not very good at it. But as a kayak coach who actually used to train people to become coaches, I'm obsessed with it. When in teaching, we have two different kinds of drills. One drill is called block practice. Coming in that, oh, I need to do this. I need to put a parallel region in the right spot, okay? So block practice, you know what you're supposed to do. You're told, this is the skill you're gonna use, do it. Okay, so it's really good at fine-tuning your communication, that you've really conveyed information. Block practice is terrible at getting information into long-term memory. There's a second kind of drill that's called random practice. Notice I have not told you anything at all about where these errors are. I have not said anything about what we have learned that is going to be responsible for these errors. This is called random practice. You're going to have to sit and think about all of this different stuff. All right. So random practice. And this is how you get things into long-term memory. So that's why this exercise is so very, very important. It's going to help move things into long-term memory. And keep that in mind when someday in the future you get to teach something. You want to make sure that every now and then you throw at your students a random practice drill. And that's what this is. So go for it. I'll leave you alone for like 10 minutes or so. I'll refill my coffee cup because it's early morning. Well, it's early-ish morning for me. But I'll be watching Discord and Zoom chat and waiting for questions. Go for it. Have fun. First thing to do, of course, is make sure you can run the program. Why don't I mute myself so you don't have to listen to my keyboard? You know, it's really interesting. I don't know what's going on, but the people behind the GCC, the GNU compilers, are amazing. I'm so impressed by those compilers. The program works. There's still bugs. I thought I'd accidentally put the solution into mandel.c. So yeah, the program works, but at any rate, there still are bugs you need to find and fix. I made sure that I didn't screw up. But if you're finding that 1.512, 1.51, there's no bug. It'd be interesting to see if that's what you get on the GPU cluster, if that compiler gives you the right answer. Yeah, but shockingly, it works. But there are still bugs in this program, so I didn't screw up.
Well, I ran it on the GPU cluster, and it definitely does not give the right answer.
Do you
Oh,
have your
good.
parallelism set to 1?
Oh, I had parallelism set to 1, yes.
I'm gonna say technically you did screw up on purpose for us to learn, so it's kind of ironically funny.
What?
Now this is weird. I'm gonna have
Wait,
to
is
dig
that the
into
correct?
this.
Wait,
Oh, wait a minute, wait a minute. You know, it's hard when you move between different shells.
no spaces. Yes.
This is
Okay, I'm
bizarre
really confused.
because it should not be working. But I'm glad that on the GPU cluster it's not working. But I verified, you know, I looked at the source code, the bugs are in there. You need to fix them. Huh. Okay. Well, I'm going to walk away for about 5 minutes or so, see if I can refill my coffee cup. Well, as usual, when you're done, you got to let me know. So if people are done, put something into the chat window so we can figure it out. So how's it going? You've been working at this for, gosh, 15 plus minutes. Has anyone found the errors? By the way, I found my error. I'm such an idiot. I was going gcc-9 mandel.c. Huh. Why no errors? Well, here's what I wasn't doing. Since I didn't turn on OpenMP, and because everything was done with pragmas, see, this is the power of OpenMP. If OpenMP is off, then it doesn't interpret the constructs, and it's still a correct working program. So yeah, I forgot the -f OpenMP. I haven't had enough coffee today to get my brain fully engaged. So, phew, my Mandel program is still broken.
Yeah,
All right.
we
Go
have
ahead.
that comment in the chat as well.
Okay, so someone used default none, which is, I kind of hinted at how useful that is. So the first thing I would do is put that there to get the compiler to help you. This is kind of an exercise in compilers. -f, OpenMP, Mandel.c. And now it tells me, oh, J is not specified. I'm sorry, I have to fix. This had, I accidentally had that default shared there. I shouldn't have. I will commit the fix. All right, so go. And it tells me J is not defined. Oh my. So now the compiler warned me about that. It's always good. I change pragma. I don't know what pragma OMP public, that's not a legitimate clause. So you get J private, that's really good. So now I compile again. Hey, that's correct. All right, someone else found another one, okay? EPS should be first private, yep. So think about it right now. I'm coming into this program, and that EPS, which is used just to perturb things a little bit, so that you're sampling the space more carefully. If I've declared it private, then it has no assigned value. So actually this operation on C is illegal. So one solution, as someone suggested, and a variable can only appear once in a data clause. So if it's going to appear, the compiler would flag this as an error. So a variable can't be in a list of more than one clause. So there we go. Hey, what does that do for me? Nope, I'm still getting the same answer. So there's more.
So
Okay.
num outside should also be declared in some way, right? Because you care about that number, no?
So num outside is a file scope variable. I declare it there. So it's a global. I want all threads to see it. I want all threads to do that count. So num outside is correctly declared. It's a global variable visible to all threads. When I declare it as a file scope variable, then it's legitimate. Can you see that? It's a shared variable. All threads can see it. And the area is determined by how many points fall outside. Aha! Making C a parameter to test point. Remember when I told you, you confuse the compiler when a file scope variable is made private. And we're doing that here. See that? C is declared up here as a file scope variable. And I'm now declaring it private. So it's that bug I showed you on the slide. So I need to go there, or keep it private. But pass it in as a parameter. And there's no reason to make it a file scope variable. No reason at all. But now I need to change test point so it takes struct d complex C. Boy, it's dangerous doing this live. And now I have to change this what was it? I think pass by value is okay. So, okay, so see what I did there? I changed it so I pass it in. All right, there's another point that someone raised in the chat that I really like. We made EPS first private, but as someone pointed out, it's read only. It could be shared. Does people see that? It's a read only variable. So you can make it first private, or you can make it shared, which means you just don't declare it. Of course, we have default none there. Let's get rid of that. We don't need it anymore. All right. So EPS could be left shared because it's read only. You don't need a separate copy. So it can be just shared instead of first private. All right. Someone else found the really big one. And I was very careful not to give this away. Num outside is okay as a shared variable. It's okay to have it file scope, but now I have a race condition, right? I have a race condition because each thread is updating a global variable. The threads are concurrent, they're unordered. That means that there's an unordered mixture of reads and writes to the same variable, and that's a data race. So I have to put something to protect that data race. Critical section. Now I am sure with all those changes I've made, I've introduced a host of bugs. I'm surprised it even compiled. But those are the big ones. And now I'm getting the right answer again. So the big changes you need is to recognize that we ran into that situation where the variable was a file scope variable and privatized. Therefore, the function, the compiler couldn't figure out how to disambiguate that. All right, that's mistake number one. So you have to change test point so you pass in the variable, the private C, as an argument. J, remember what I said, the OpenMP parallel 4, the OpenMP 4, it will privatize the loop control index of the parallel loop, but not any embedded loops. So you had to make J private. Now, EPS is an interesting case. You could leave it shared, or you could make it first private. And both are correct. If you leave it shared, it in principle sits on a cache line, and I can have a false sharing situation again. It can get really confusing. Any reasonable compiler would take that variable EPS and promote it to a register and just leave it there. So the performance of leaving it shared should be the same as first private. But if your compiler is doing stupid things and doesn't pick up on that, it would be slower to leave it shared than to make it first private. But the solution of just making EPS shared works fine. The big one is you had a data race on num outside, and you had to protect that with a critical. Now, remember, if you think about it, I'm now putting a critical inside a doubly nested loop. And when we talked about critical earlier, we said, don't ever do that. You put a critical inside a loop, it can be a mess. Except each thread is going to be going through up to max iteration times until they hit the divergence of the Mandelbrot set. So the chances of two threads hitting that critical at the same time are hopefully low. We call it, so the jargon here is critical sections and synchronization constructs like that are implemented with locks. And so we say that it's an uncontended lock. It's an uncontended critical. It's not likely that two threads are going to hit that critical at the same time. Does that make sense? He says, looking around the room. Oh yeah, everyone's getting that. Cool. So this solution works. But when I said that those of you who finished early, try different optimizations, there are other ways to handle that num outside that do not involve a critical. And if tonight or later on today you want to dink around and try out some different ideas, this is a good exercise to go back to and think about what you can do based on what we've learned to optimize this code. There's several things you can do. One of which is dealing with that num outside increment without using a critical. And I won't say that because I want you to figure it out. I'm now looking at the Discord comments. Yeah, the bottom line is in the C programming language, there's very few, if any, situations where a file scope variable makes sense. It's just avoid them. It works for num outside. Okay, yeah, I really want that shared everywhere. But it's just, they should be used extremely rarely. So C needs to be private. Yeah, remember, if in OpenMP, it's important to understand this. OpenMP is built in C around pragmas. If a compiler doesn't recognize a pragma, it just skips it. It just ignores it. This is incredibly powerful because it means if I don't put -f OpenMP in my compiler line, then I just run it as a regular serial program. And therefore, none of these errors came up. And that's why earlier when I was running the program, I forgot it. So remember, I is made private by default because it's the loop that is affected by the OMP parallel 4. So if for the loop that you are parallelizing, and here we're just parallelizing I, that loop control index is made private by default. Now, I will sometimes, in my own code, declare it private anyway. Advice from an old guy, okay? I write my programs for the person reading it. Early in my career as a graduate student, I was developing these new numerical methods for large systems of coupled Schrodinger equations. It was more math than physics, but it was cool. And I had calculations I was doing, and we had primitive computers. They would take days, if not weeks, to run. And I had to throw away 6 months worth of calculations because I lost track of which data corresponded to which program. And since I didn't know, it became scientifically invalid and I had to throw it all away. And I learned a painful, painful, painful lesson from that. Everything, whether it's the collecting and organizing data to the code you write, everything, write it and document it as you're writing it such that you could come back to it 6 to 12 months later and know what you did. So you write code for the reader, not the programmer. And we got some cynics online here. Okay, yes. All right. I would love to spend more time talking about this. This is a juicy exercise, but we have to move on. I have a short section here that's important to go through. And then I guess in 20 minutes, we take our first real break, I believe. All right, memory models. And I get real dramatic here. Stand in the center of the room and I say, all right, you all know where the exits are, right? Okay, we are now going to talk about memory models. And then I look and I see who runs for the exit. Memory models can be a friggin' mess. The computer science of multi-threaded programming, when it touches on the memory model, it gets thick and ugly and, oh my God, awful really fast. Okay, so here we go. Yeah, running for the exit. Think about a modern CPU. All right, I have my cores, which has a control unit, an arithmetic logic unit, and they run out of the register file, which is these tiny, tiny little memory region that runs at the CPU speed. Then I have my cache, level 1 cache that's right there with the core. And then those caches share another cache, which then go off to DRAM. And sometimes, like on the Xeons on the GPU cluster you're using, this is a laptop CPU, there's even another level of cache. So you have all these multiple levels of cache and then memory. So think of the variable gamma. Remember, a variable is just a name for a location in memory. And when I say memory there, I mean in DRAM. In fact, I'll use the word DRAM here just to disambiguate. A variable is a name for a location in DRAM. So let's think about gamma. Well, because of the cache coherency protocol, it maintains sort of a cache as a window into memory that moves that view of memory close to the cores. And so I may have a value of gamma sitting in the shared last level cache. If each of the cores are working on it, they may have a copy of gamma in their level 1 caches. And remember, compilers aggressively promote variables into the register file because it still costs something to go back and forth to cache. And if you're using it again and again and again and again, like that EPS variable in the Mandelbrot program, it may just leave it in the register file and not go back to cache at all. So now the question is, I do a read of gamma, and what value do you get? Load gamma. Okay, I'm core 2, load gamma. Which value do I get? So what a memory model does is it defines the rules that state unambiguously, because we're talking about we got to make things work for compiler writers and computer architects. It defines unambiguously what values of gamma you're allowed to read. Sounds easy until you look at all the different places it can come from. So this is called a memory consistency model, or we often call it a memory model for short. And they're the rules you use for getting the right value. Now, I could go into a long anecdote about why this is so awful and why this is so scary. Let's just say it's taken, to get to the memory models we use today, it's taken 10 years plus, maybe 15 years of work by the greatest computer scientists of their generation to finally produce a memory model that usually works. Even the memory model, the best memory models we have today have cases where they break down. So this is a very difficult area to get right. And I say this with the battle wounds still littered around my body, because I led the effort to write the memory model for OpenCL. So I've been a frontline warrior in this. So well, we got to keep it simple. Any multi-threaded programming model, any, and so it includes OpenMP, in order to be implementable, uses what's called a relaxed consistency memory model. What that means is the view of a variable gamma, like we saw in the previous slide, could be different between threads. So threads maintain a temporary view of a variable, and that temporary view of the variable may, at any given point, be different across the threads. All right? So you need points in a program where you say, wait a minute, guys, wait a minute. Okay, all of you, you need to agree on this value. I'm sorry, all of you, you know, we need to make the temporary view consistent with the view in DRAM. We've got to do that. So we have an operation in OpenMP called flush. And that's what flush does. Flush is called by a thread, and it's a way for the thread to say, for this variable, or for all my shared variables, update them in DRAM so that everyone can see a consistent view. All right? So getting a little bit more jargony, it defines a sequence point, and in compiler jargon, the statements in your program break down into a collection of specific smaller operations, and each operation defines a sequence point. So it defines a sequence point in the program where the thread has said, I have made my view of these variables consistent. And what that means is, for those variables, and we call that the flush set, all reads and writes to that variable are complete, and they're visible to other threads. And in my program, me, the thread that's calling this, in my sequence of operations, no subsequent reads and writes of that thread have occurred. All right, so it's a way of saying that, hey, I'm making my variables consistent for me, from my view. All right, so it looks like this, and this is an example of where you might want to use it. I have a variable A. I'm going to compute on A, and A is shared. Okay, so imagine A is shared. I'm going to do a computation on A. And now, before I go on and do anything, I want to make sure that everybody's had a chance to see that value of A. So then I do the flush. Now, I want to be clear. Flush doesn't say anything about the other threads. It does not define a synchronization point. It's used in this way. Okay? It just says that make my view consistent with other threads. Now, what makes this so complicated? You may be going out, why are you going on like this? Why, this is just boring. Let me tell you why. Compilers reorder instructions. And you have to think about this when you're talking about multi-threaded programming. A compiler reorders instructions, and a compiler only knows, in the base language, a compiler only knows its core base language. So it could move past, you know, it guarantees that you'll get the right result from sequential execution, but it knows nothing about the other threads. So you can cause all sorts of chaos. So the flushes limit the movement of instructions around points in a program. So you can use this to force consistency around different variables. I've gone on way too far, but I just want you to be aware of this, that there are these low-level constructs in OpenMP that you need to deal with sometimes if you're building very low-level synchronization protocols. And what we do in OpenMP is we try and imagine when you need a flush, and we put them in there for you. So we imply a flush when you enter a parallel region and exit a parallel region. Anywhere there's a barrier, either implicit or explicit, we do a full flush. When you enter a critical region, when you exit a critical region, we do a full flush. Okay? So we try and do flushes where we think you need them. And therefore, I want you to be aware they exist But if you use these high-level constructs, critical, barrier, exit of a parallel region, and if you do all your synchronization, so ordering on data, all your synchronization that way, you never have to think about a flush. But if you want to start doing some wonkier synchronization, like I want to do pairwise synchronization, so I have 10 threads in my team and I want thread 7 to wait until thread 4 is done with something before they go on. At that point, you're doing point-to-point synchronization. At that point, you have threads having to exchange information. At that point, you need to write code with explicit flushes. So let me tell you, if that ever happens, do not try to do it yourself. Do not pull out my book and read about memory models and then try and write the code yourself. I mean, read about memory models in my book, it's really good, but don't write that code yourself. Get an expert, because even the experts get it wrong. So you need to be aware that point-to-point synchronization, that all the plumbing in OpenMP you need to do these weird, any synchronization, ordering of threads that you need to do, it's there, it's available to you, you can do it, but leave it to the professionals. It's ugly. Stick to the high-level stuff. Okay, now we're coming now to near the end. So let me talk very quickly. We're gonna have to shift because we're running out of time and I don't want to skip on, I really want to reserve my last 90 minutes with you for MPI and GPUs. So think about this problem. I have a list and I have a pointer to the head of the list, and then I'm going to walk that list. So while I'm not at the end of that list, I will do the processing associated with that element of the list, and then I'll increment to the next. So P points to the next value. It's a little bit more C syntax than some of you may be used to. But I think you can see how this works. I have a list, and the list consists of a value and a pointer to the next item in the list. And I'm going to use a while loop to walk the list. So, we don't do this in array type programming. So many of you go your whole life without writing code like this. But there are a lot of problems that have this kind of irregular structure. You can't map it into a regular array indexing scheme. So I need to walk a list, or I need to use a while loop. The while loop, I don't know dynamically. I can't write a closed form expression for how I can break up a while loop between threads. So there is no parallelize this while loop construct in OpenMP. So it's all dynamic. It's all, oh my God, what am I going to do? Okay, so nothing we've done so far can help you do that. So the first thing I do is I give people, in the long version of this course, I have a lot of fun telling people, and actually I urge you to do this. In the exercises, let me verify that this version has it. Yeah, linked.c, all right? We're not going to do it now, but the file linked.c walks a linked list and does a computation for each item in the linked list. So it's a fun exercise, especially for those of you who are really enjoying OpenMP and want something to play with on your own after we're done. Parallelize linked list using everything we've talked to up till now. Just parallel and parallel loops, okay? Using a parallel construct with the SPMD pattern or the parallel loops, can you parallelize linked list? And the crux of the calculation comes down to this while loop right here. And it's ugly. It's really, really hard. And it's another one of these random practice drills. It's like, how do I do that? What do I use? All right. And I give the solution here, but I'll skip it because we're running out of time. So it is so ugly to do code like that we realized we had to add something else to OpenMP. We added the idea of a task. So a task is an independent unit of work and the data environment associated with that task. So think about, I have 3 tasks here, the pink, the green, the purple, And I package each one of them up and I throw them in a queue to execute in parallel. And it's a very flexible structure for expressing the concurrency in my problem. And then I can run through the task queues to execute them in parallel. And it allows me to expand OpenMP to cases where I just don't have a simple loop. I have something more complicated than a loop. All right, so that's how the task constructs work. And they're very powerful. So there's a common, okay, yeah. There's one more thing I have to introduce before I start showing you code that's working with a task. And this is another work share construct called single. And I apologize, we're in lecture mode now, but we're running out of time. So I'm sorry I have to slip into lecture mode. Because normally I'd give you an exercise to use a task just all by itself. There are times you want your team of threads, you want one thread to do something while the others wait. So you're still splitting up work in the parallel region. So it's technically a work sharing construct. And so it's a work sharing construct called single. And what single says is one thread will do the work in that structured block. The other threads will wait right here at the end. Remember, in work sharing constructs, they imply a barrier. So pragma O, and this is a pattern that happens in a lot of differential equation solvers. You do a lot of work on the interior, and then you have some complex, messy boundary exchange. And especially when you're first debugging the code, it's really, really hard to get that messiness done right. So you say, look, all of you wait, one thread will take care of the boundaries and exchange all the boundaries and set all the boundary conditions. Okay, then everyone else goes on and does the next phase. So it's a very common pattern. So this is where I might use single. So the standard pattern in working with tasks, you create a task with pragma OMP task. And once again, it's a structured block. And a structured, one line is a structured block of one line. If I need multiple lines, I do brackets, right? You're all familiar with that now. So here's the common pattern you see. Pragma OMP parallel. And you don't get multiple threads without the parallel. Then I have one thread walk through the creation of the tasks. The other threads will be waiting at the barrier on that single. So that's where I have that red arrow pointing, is the barrier on the single. So that one thread, the one that's going to do the single, and you don't know which one, you're just saying, hey, one of you guys do this. Everyone else, wait at the barrier. So one thread's going to hit pragma OMP task, so it'll package up the function thread. It'll capture the data environment so that thread will know what to do. It'll do that for Daisy. It'll do that for Billy. And then the other tasks sitting there waiting at the barrier will start executing thread, Daisy, and Billy. Nobody moves past that barrier until everyone's finished the work. And tasks can be nested. Fred, Daisy, and Billy can each create additional tasks. In fact, commonly they do. So therefore, I have all of the tasks, including the ones inside Fred and Daisy, will complete before anyone leaves that barrier. And that's how tasks work. And so you create the threads, one thread packages the tasks, and then they're going to execute in some order. So then I give you a simple exercise. I'm going to skip it because once again, those of you who want to play with it, you have the exercises, you have the slides, go play. The data scoping, the way the data works on tasks is pretty much just what you've learned, except there's one little extra. If you think about it, when you encounter a task, a thread can just execute it, or the thread can put it on a queue for later execution. We say that the task has been deferred. All right, so what's the data environment it sees? So what it does is it captures the environment at the time it was created. That's important. If you think about Fred, Daisy, and Billy from the previous slide, you know, when it's time for them to compute, we're still talking about OpenMP. There's shared variables, there's private variables. Okay, So you're going to capture the variables at the time it's created. Now, first private becomes very critical to a task. And so the first private on a construct, it'll take the original variable at the time the task was encountered. It will capture its value and save it in a private variable on that task. So first private becomes very important on tasks. Okay, so here we go. It's so important that if a variable is private already, we will make it first private for the task. So here I go, I have pragma OMP parallel. I have a variable that's shared A. I have a variable B that's private. So now I come into my code and I create a task. So inside this task, so you know what's the state of the variables that that function compute's going to see when it runs. Okay, A is shared. It's no different than it's ever been for you in OpenMP before. It's a shared variable. All the tasks are manipulating the same shared variable. C is obviously private. I declared it inside this task. It's on the stack of the task. It's clearly private. B, in OpenMP, we try really hard to anticipate the common sources of error you're going to run into and make the default case safe. So if the original variable is private when you encounter the task, which you see is the case with B, isn't it? When you're cruising along and you hit that task, B is a private variable. We're assuming what you probably meant was to capture that value. So you probably meant that to be first private on the task. So I could type right here, first private B, to create a private on the task and make its value and capture its value. But we decide that no, you really want that by default. So when you get to compute, B is first private. I went through this so slowly because it's different than you've seen before. All right. So then I ask you using tasks to parallelize the linked list. And I'm going to go ahead and show that code. It's delightfully simple, actually. Remember that original code. I just had a while loop over my list. And I did the processing at each point and then went to the next. All I have to do is I create a single around that whole while loop. One thread walks the while loop and fills up all the tasks. And then all the other threads wait at the barrier and do the computing on the task. Now, there is a lot more. You now know enough to work with tasks. There's one little detail I want to talk. We're almost done. I know we're 2 minutes into your promised break, but we're coming. We'll use it. I want to finish this. So when do you control when tasks complete? So remember, at a task barrier, all the tasks, included embedded tasks, complete. Sometimes you just want the tasks at the same level in the program, the tasks in the same scope that were created with explicit tasks in the same scope. You want them to finish. That's what the task wait. So here, I got my arrows, so, geesh. So at any rate, I have my single. I'm going to create Fred, Daisy, and Billy, but imagine I don't want Billy to run until Fred and Daisy are done. So that's where I would use a task wait. So task wait says for the tasks at the same level, at the same scope, right? So in other words, task wait says wait for Fred and Daisy, but if Fred and Daisy create tasks internally, don't wait on those. Don't care about those. So a barrier would care about those, but this case here, task wait, it just cares on when is the task Fred done, when is the task Daisy done. I hope that's clear. So I'm going to show you the prototypical example of that, and then I'm going to wrap up and we'll be done with OpenMP. Yes?
If we go back to the previous slide where we're doing the task wait, you mentioned that Fred and Daisy can create tasks of their own. So those they're launched independently of the completion of Daisy, so that so that Daisy's execution is considered complete once it is finished spawning all of its other tasks?
Potentially, yes, unless I
Okay.
put a task wait inside Daisy.
Okay. I just
Yeah,
wanted to clarify. So in other words, a an a task completes when it is finished doing its computations and launching all other tasks. It does not wait. So Daisy does
and
not wait for all of its subtasks to complete.
unless Daisy includes a task wait. Yeah,
Got it. Thank
yeah.
you.
And this is important, and I know this is subtle, and I know we're rushing this. You know, clearly they could just turn this whole week over to me and I would fill it easily. Because we could spend an entire day on tasks. It opens up a whole vast vista of parallel computing options. And I want you to be aware of them. The fact of the matter is that most people doing scientific computing, because we tend to discretize a domain, and then whether it's, you know, finite element, finite volume, you know, finite difference, we tend to do things loop oriented. But there's an awful lot in the world that just doesn't map onto loops, and tasks allow us to get at those through OpenMP. So a lot of these questions will become clear when I give this example. And what I'm planning to do here, because I'm sure you've been sitting and listening to me for so long, hopefully you stretched your legs during the Mandelbrot exercise. At 45 minutes past the hour, I will stop with OpenMP. We will take a 15-minute break, and then we will spend the last 90 minutes on MPI and GPUs. But I want to show you this example, because this is like a prototypical example of how you would use tasks. Here is a really stupid way to generate Fibonacci numbers. It's a recursive algorithm. This is, you know, when you give a computer science lecture on recursive algorithms, this is the one they use. And you all know what a Fibonacci sequence is. You know, the generator function is f at n equals f at n minus 1 plus f at n minus 2. This is an n squared recursive algorithm. It sucks, but it's great for showing recursive algorithms that fit on one PowerPoint slide. So, you know, I just take that generator function, that recursion relation, and directly turn it into code. All right. So I have my main program, and I call my recursive Fibonacci function with the Fibonacci number I want. And then I have an exit condition. I don't remember if I have a build. No. Okay. If n is less than 2, I just return n, because that's how you seed the recursion. So that's my exit condition. When is the problem so small I can just directly compute it? Okay, then I recursively call Fibonacci in n minus 1 and on n minus 2, and I return that sum. So this is a recursive algorithm for returning a Fibonacci number. All right, really cool. So here's how I would parallelize this with tasks. And I want to walk through this because this is a pattern that comes up a lot. And remember me, I'm all about patterns, because once you know the pattern, you can carry that knowledge to any programming model. And so becoming an expert parallel programmer means you learn the patterns. So I'm going to create a team of threads to do this recursive function fib. One thread, so I have a pragma-OMP single, starts the recursion. So it does the first call to fib NW. Now I come inside my Fibonacci sequence function, and that one thread with the single is going to see and create, it's going to test and say, are we done? If not, okay, I'm going to create a task. Fib at n minus 1, fib at n minus 2. So it creates 2 tasks. Then I wait, because I want to wait until those tasks complete and sum the result. And this will give me a parallel task-oriented program. And there's a picture that explains this. And this is an incredibly important pattern in parallel programming. Once again, some of you may never see need for this, but there's an awful lot of optimization problems, an awful lot of data analytics comes down to this pattern. So it's something you should be aware of. It's called divide and conquer. Oh, this is how we do FFTs. All right, that's, if you think, you know, if you know about how FFT is implemented, one of the common ways to implement an FFT is this way as well. So you have some way to split a problem into subproblems. And so you have a split function that splits the problem into two subproblems. And you recursively keep splitting. See, that's just how we did with the Fibonacci sequence. You know, you recursively keep split, until the problem gets so small you can directly solve it. Then after you solve it, you can have a way to merge the subsolutions together. So with the divide and conquer pattern, there's always a split approach. There's always a direct solve, and there's always a merge. And each one of those is an opportunity for exploiting the parallelism. So if you look right here, this is my direct solve. This is my solve subproblem. When is n less than 2? Just return n. My split is the task creation. Okay, I have a task on n minus 1, a task on n minus 2. So that's my split. And I'm going to wait until those two are done until I start getting solutions. And then when they're done, my merge is at x plus y. And notice I had to make x and y shared so that the values existed after the task's finished. Because remember, you go out of scope, a variable goes away. There's so many layers of details here. I understand. You know, you're going to have to play with this in order to really nail it down. But that's a direct solution of this problem. And there's so much more I can say, but the exercise for those of you tonight who want to play with this one's fun. This one's really fun. Take that original Pi program, pi.c, make a copy of it. And first off, create a recursive algorithm for processing that loop. That's a fun one there. Then after you have that recursive algorithm for processing that loop, parallelize it with tasks using the divide and conquer algorithm. Anytime you hear someone talk about a cache oblivious algorithm, that's what they're doing. And I'm sorry, I have to say, and that's all there is on tasks, because I have to wrap up. But I'll be available for questions and you know, during the break and all of that. So now let me move past all of this and do the recap. So we have covered some in slow detail, but we have covered all of these. And I assert that most of you, this is all of OpenMP you will ever need to use. But I will also assert that once you truly master this list of the Common Core, you will have the background you need to go beyond the Common Core and learn the other features in OpenMP. If you try and just start at the beginning of OpenMP and learn everything all the way through, you will give up in frustration. So the way to learn OpenMP is give yourself lots of problems to work on and master these constructs, and then go back. Okay, yeah, there'll be hours of fun tonight. That recursive Pi will be a blast if you don't have experience with recursive algorithms. But I want to emphasize there, when I say that the Common Core is almost all you need, that's true, but there is a lot more, and at some point they do become valuable. You know, if you write lots of multi-threaded code, you will come up with a situation where you need more advanced synchronization. That will come up eventually. Critical and barrier don't quite do it all. So at some point you will run into situations where you need more synchronization, and it exists, it's out there. There's a few other of these data management clauses we didn't talk about. Last private, thread private. Tasks. We introduced tasks and explained how they worked and gave you enough to do basic tasking. It would be an all-day course just to cover everything that's there with tasks. But there's more there. There are these vectorization constructs. I'm going to say something that this is being recorded, but that's okay. Intel may hear it and discipline me. That's okay. I don't care. I don't use the vectorization constructs. Intel loves them because Intel depends on you making good use of the vectorization unit. If the compiler doesn't give you enough vectorization, then you're probably just screwed, but they're all there. And that was very much non-kosher by Intel standards, because we love vector units. And then I will say a little bit later on, but we've added the ability for you to program your GPU from within OpenMP. So There is a lot there. The spec is moving so fast, and specs are written for compiler implementers, not programmers like you. So the books available for OpenMP are really critical. So let me just emphasize, here's just a longer recap is all this is. There are a lot of resources for learning OpenMP. So you can go to www.openmp.org and find all the specs, but you don't learn by reading the spec. But look, for each spec, there's an examples document. This is valuable because they've done a pretty good job of every single construct in OpenMP. They have an example of it. So you learn the spec by getting the spec and getting the examples document and moving back and forth. Of course, I have a book, and of course, I think you should all buy it because you love it. So look, this is the best book out there, and it's modern and up to date compared to the other books for learning OpenMP. So this is the book to start with. Once you've got past the start, like, if you learned everything you need in this tutorial, you don't need any more introduction. This is the book to get. So for many of you, if this tutorial, this discussion we've done was like, oh yeah, I got it. Oh, I got all that. Yeah, that's easy. Go straight to this book. Ruud van der Pas, Eric, and Christian have done it's a wonderful book. It doesn't cover the OpenMP 4.5 and 5.0, but frankly, a lot of the stuff in those specs people don't use anyway yet. And that's it. Oh, of course, there's also my other book, Patterns for Parallel Programming. That's old and out of date, though. So thank you very much. That completes OpenMP. We will start at 1 minute past the top of the hour, and we will go through a quick survey of MPI and GPUs.